Hello, scholars. Our objectives here are to use stoichiometry, the quantitative relationship between reactants and products in chemical reactions, to answer chemistry questions. And we use dimensional analysis as a procedure to accomplish number one. Now, stoichiometry, we've heard that word. It's a fun word to say. It's a new word for many of us. And it involves using the conversion factors necessary to relate among reactants and products in a balanced chemical equation. And the technique we use to incorporate those conversions is this problem-solving technique that's valuable to use for all types of problems in systematically driving to a solution. That's dimensional analysis. The conversion factors, the main ones we've been using in chemistry, is these right here on the bottom, where moles is the central international quantity of matter. Amounts of matter are really moles, because in chemistry we think about and consider way down to the atomic level. And to do that, and to solve problems and think about it practically, we need to think about from the moles into grams. Grams are things we can weigh, so we need that relationship between grams and moles. And also, if we're curious and thinking at the atomic level, individual atoms or individual molecules or individual formula units, we use this conversion factor of Avogadro's number. This is a curious question I posed a few days ago. How long would it take to count to 1 billion? There are very good, interesting answers. Some not too thoughtful, but many thoughtful, and gave reasons how you would do this. That's what I asked. Well, here's a way to use dimensional analysis to solve this. In fact, some scholars did talk about a dimensional analysis type solution. So here, for dimensional analysis, we set up this bridge. Sometimes we need several of these planks in the bridge. These represent the conversion factors that we'll use. In this case, count to 1 billion. So we think about that. There's a big number, 1 billion. Kind of hard to think about and put in context and relate to things that we normally think about and talk about. So that's a place for dimensional analysis, to put it into a unit that we can relate to. So here's how a way to do this. So we put down the amount that we have. In this case, we're talking about counting to 1 billion. And then we want to get to something that we can kind of relate to over here at the end. All right, so let's first we need to kind of define what we mean by count, put it in some time unit. Let's say we're just counting, not too quickly, just counting at a second per count. So like 1, 1,000, 2, 1,000, or 1 Mississippi, 2 Mississippi. Those are counts at about 1 second. We could probably count faster, but let's take this. So we made some assumption here. That's the conversion factor, 1 second per 1 count. So now we reduced and changed the what we have from counts. Now we're talking about seconds. At least seconds is a unit of measurement that we're more kind of can visualize, but 1 billion of them, hard to do that. So let's do another conversion factor. We know that there's 60 seconds in a minute, and along the way you see that we're canceling out units and get to the next unit. So we're at minutes now. It's probably a lot of minutes that we still can't really kind of conceive realistically. Okay, so now let's put it into hours. You know where we're going with this, hours. and put it into days. Along the way, we're always canceling out. We're putting the conversion factor in a way that we can cancel out the previous unit and get to the brand new unit. Okay, so we're at days. It's probably still a lot of days, so let's do that final conversion. And now we've put it into years. So along the way, we've used conversion factors that we know are true. We made this first assumption over here of a second per count, and now that we have just the final unit, that's we're agreed that a year is something we can conceive, we can get our mind around. We know about what a year means, and solve the problem. So we're going to multiply everything on the top. Well, it's multiply that, it's 1 billion on the top, and we're going to divide it by the product of the bottom. So that's 60 times 60 times 24 times 365. That's going to be in the denominator. We divide that into the 1 billion. And we come out with about 32 years. Right? It's an estimate, plus or minus. We're not super accurate, but at least we got this. It's within this time frame, a year. So if you count a little faster, if say you count 2 counts per second, you can cut this in half to 16 years. Still, it's a long time to be counting. Right? So that's a kind of a use of dimensional analysis, not really super important, but it's a good kind of practice, that problem-solving approach, because now we're going to use that in some chemistry problems. As you've worked the 9 questions already, and you may have had some success, maybe not. That's why we want to talk through them right now. So stoichiometry again. So this is a little figure showing how we can go back and forth with our conversion factors. Mass is something that's readily measurable. If we're going to use that to calculate something else, mass of, say, iron or something, and we want to figure out what, if iron reacts with something, how much of that other reactant is going to produce what product, we need to go through this kind of thing, a mole basis. So molar mass is that conversion factor. You can see here, we could flip it, put a mole on the top or a mole on the bottom, depending on how we're going to work through the dimensional analysis. If we want to know about individual particles, then we use Avogadro's number, because there's that huge number, 6.02 times 10 to the 23rd, number of those particles, whatever we're talking about, whether it's iron, ferric oxide particles, or oxygen molecules, or water molecules, whatever, there's always going to be this number, Avogadro's number, in 1 mole. If we have a gas at standard temperature and pressure, which is 0 degrees C and 1 atmosphere, then 1 mole of it always has a volume of 22.4 liters. So if we wanted to make that conversion in a question or a problem, that one is we use in the dimensional analysis. So here's an example of a balanced equation of iron and molecular oxygen forming ferric oxide. Ferric oxide, we recognize that as rust. So rust on this wrench. Now, this is a balanced equation. You can see here there's four equivalent moles or individual atoms of iron on the reactant side. And you can see on the product side there's 2 times 4, there's 4 over here. Oxygen, there's a total of 6 oxygens on the reactants and 6 in the products, right? So we did balancing equations a while ago. So that's what you have to have, a balanced equation to do this. So and many of the questions that are asked are looking at a balanced equation, and given to us, say it could be given to us mass or number of particles or maybe even volume, and we may have to go use these conversion factors to answer the question. So here's the little sketch that we had from a while ago when we introduced a mole is equal to that many particles. These could be, again, it could be atoms, it could be ions, it could be molecules, it could be formula units in chemistry, or something crazy like 1 mole of bananas is 6.02 times 10 to the 23rd bananas. Right? It's just a unit, like a dozen is 12. 1 mole also is equal to molar mass of whatever we're talking about in grams. Molar mass. So what is molar mass? That's the mass of 1 mole of the substance that we're talking about. And we get this number from the periodic table, from the individual atoms of elements that make up the substance that we're talking about, whether it's magnesium sulfate, or whether it's HCl or sulfuric acid, whatever. It has a different molar mass. That's the mass of 1 mole of that substance. And here again we're showing the relationships between going from grams to mole. We use molar mass, and from particles we use Avogadro's number. And when we use them in dimensional analysis, we're going to be using them as these equivalencies or conversion factors. They kind of look like a fraction, right? But they're equivalents. 1 mole is equal to molar mass of a particular substance, and 1 mole is equal to 6.02 times 10 to the 23rd particles of that substance. And it's the same, flipped up and flipped the other way. Still, it's that the equivalency. So putting together reaction stoichiometry, just to clarify the definition here, the stoichiometry deals with the amount of reactants and products in chemical reactions. The mole ratio is that conversion factor that relates to the number of moles of any 2 substances involved in the chemical reaction. Right? Any 2 of them. So for instance, the mole ratio of iron to oxygen, the mole ratio is 4 to 3. The mole ratio of iron to the rust product ferric oxide is 4 to 2. That's the more practical we think of moles, because moles have enough mass that we can weigh them, we could see them. But it also, we could think of it at the molecular level, atomic level, that 4 atoms of iron reacting with 3 molecules of oxygen, making 2 formula units of ferric oxide. Right? So that's thinking at it at the atomic or molecular level. This diagram shows us in a little more detail. If we need to go from a mass of, say, the iron, and we're asked about the ferric oxide, we need to make these kind of steps. We have to go from mass of the iron to moles of the iron, and then moles of the iron to the moles of the ferric oxide. That's where that mole ratio comes in. And then from the moles that we have here of the ferric oxide to the mass of the ferric oxide. Or if we're asked about individual formula units, particles, then we'd use this conversion factor. And so now to come to these questions that you worked on, I'm going to go over them in detail here, that you completed in that Google form, but let's talk about them here step by step. How many atoms would you need to count to have 35.75 grams of silver? How many atoms? So when we say atoms, number of atoms, we know that Avogadro's number is going to be involved here. And we have the silver in grams. So we cannot go directly from grams of silver to number of atoms of silver. We need to go to moles first, and then to atoms of silver. So the first conversion factor, we would want to get to moles of silver. So that's the molar mass of silver, and we get that from the periodic table. 1 mole of silver, you could check and look in the periodic table, you should be able to find it. It's 106.9 grams per 1 mole of silver. So now we're able to go from the grams to the moles, and then a final conversion factor, we need to go from moles of silver to individual atoms. And then we're able to cancel out the units and see that the units we have left is really what we were trying to figure out, and that's atoms of silver. Now it's once we have this set up, now we can enter into our calculator. And really do need to know, you don't want to set all this up and not get to an answer that you could check and see if it's reasonable. So you do need to know how to use the calculator that you're using. That is, know how to put in this little exponent here. Gave you a little guide on how to do that. Okay, and so multiply the top and divide it by the bottom, and you come out with 1.995 times 10 to the 23rd atoms of silver. So it's kind of not a real practical problem, but it's exercising you knowing how to use dimensional analysis and answer an interesting question. Okay. Now, as far as how many digits we put here, you don't want to put all the digits. You don't want to put all the digits that the calculator shows. We need to say, okay, I need this many digits, because we should be informed by the number that we're given right here. There's 4 digits, and that's what we should round the answer to, 4 digits in the final answer. We use the number that has the least number of digits. That's the measurement that has the least number of digits to guide us in how we round the number in the final answer. Okay, next one. What is the mass of 3.56 moles of strontium bromide? Okay, so we're going back to think about what is that. Here's strontium bromide. Strontium is a group 2 metal, alkali earth metal. Being in group 2, it has 2 valence electrons. Loses those electrons, becomes 2+. And bromide, or bromine, becomes bromide when it becomes an ion. You might remember, this is in group 7A, 7 valence electrons, and it's a non-metal, so it gains 1, becomes a -1. And that's where we have 2 -1s combining with this 2+ metal, and that's the ionic compound, strontium bromide. We change bromine to bromide when it's in an ionic compound. Alright, we'll review there. We have this many moles, so that's the first thing we put on our little dimensional analysis bridge. And now what do we need? We're trying to get to mass. So we have moles, we want to get to mass. If you look on the little diagram there, we're going to use molar mass to do that conversion. Now it's a matter of which way do we put that molar mass over here. We want grams per mole. We're going to look it up in the periodic table. We need to look up the molar mass of the strontium, molar mass of bromine times 2, add that up, and we're going to put that on top because we want grams in our answer. That was the question. What's the mass? Okay. So we have grams on the top, moles on the bottom, and now we can cancel the moles and then multiply across and come up with the answer is 881 grams of strontium bromide. So if you didn't have that answer that way, then make your corrections, because we see that it cancels out and gets us to. And why do we put 3 significant figures here? Because that's our measurement over here with 3 significant figures. And we're all happy when we get that right answer, jumping for joy. Okay, which weighs more? 7.65 moles of sulfuric acid, H2SO4, or 7.89 times 10 to the 24th formula units, that's what we use for ionic compounds, formula units of copper 2 chloride. Copper 2 chloride, so copper 2 means copper is in a 2 plus oxidation state, and chloride are minus 1s, and that's why there's 2 of them. Copper chloride, that's the formula. So you needed to know that. If this wasn't given, you should be able to figure that out from the name. Alright, so we will do the first one first. We have 7.65 moles of sulfuric acid. We write that there. We want to make sure that we write the full number along with the units and the substance as we put it on our dimensional analysis bridge. Now, we want to get to mass, so we need a molar mass conversion here. We need to figure out, we go to the periodic table to get the molar mass of sulfuric acid, H2SO4. We add carefully, we add up, hydrogen is 1.0, sulfur and 4 oxygens, add that up, come out with the molar mass of sulfuric acid, which is 98.1 grams per 1 mole. I notice we put the moles on the bottom so we can cancel that out and get to grams. Now we just multiply across the top, divide by 1, come out with 750 grams of sulfuric acid. Now, this is 3 significant figures here, so our answer should be 3 significant figures, and that's why, so this is displayed as 3 significant figures. To make sure that we are saying that it's accurate to the ones place, we put a little decimal point there. So those are 3 significant figures. Now we have the grams of sulfuric acid. Now we have to figure out what's the mass of the copper chloride. So we put the copper chloride there, that many formula units of copper chloride, and now we need to go from the number of particles to moles, which will involve Avogadro's number. 6.02 times 10 to the 23rd per mole. We're going to go from number of particles to moles and then to grams. Okay, so here we're making the conversion. We're going to get rid of the formula units. Now we are in moles. Now we go moles to grams like we did up here. So there's an extra step in this solution. So now we added up, the copper chloride weighs 134.6 grams per mole. Cancel out those moles, and now multiply across. So I really want you to know how to use your calculator. If you're having some trouble with that, please get some help. I'll help you with that, or look at the guidance that I posted on this, and multiply that, divide by this. This will be a good test if you really know how to put these numbers into your calculator, exponents. And we come out with 1,760 grams of copper chloride. So that was rounded to 3 significant figures. We didn't do a whole lot with significant figures, but I'm reminding you about them right now. I'm not going to hold you to the getting this right all the time, but I'm mentioning it along the way. There were 3 significant figures over here, so this number has 3 significant figures. This 0 is considered a placeholder, so we rounded it to the 10th place to express it in 3 significant figures. Alright, so This answers our question. It's the copper chloride that weighs more. Put a circle around it. That was the question, one of the questions. And then it also said how much more. So part of practicing and doing problems and practicing things is reading the directions and answering questions completely. It'll pay off in lots of things that you do. So the rest of the question was, what's the difference? So we subtract the amount of grams of sulfuric acid from the other product, the copper chloride, come out with 1,010 grams. And we're happy about that. Solution is very clear, boxed in right answers, made circles, very clear. So you do want to practice writing this all out. Right? It's building skills of writing, solving questions, and being successful. Number 4, how many moles of oxygen will be formed from 1.65 moles of potassium chloride? Potassium chloride. Okay, so here we're given the balanced equation. You could check that. There's 2 potassiums, 2 chlorides, 3, it's 6 oxygens and 6 oxygens here. Okay, yes, a balanced equation. So this is what we're given. That's the first thing that's going to go on our dimensional analysis bridge here. Put that there. So if you're wondering, when we put this in the dimensional analysis format here, it's as if there's a 1 down here. You don't have to put that. So I know when you're first learning dimensional analysis, it's a little confusing and you don't like how this looks, that nothing is down here. But just imagine there's an imaginary 1 there. But this is a very robust, great way to solve problems. You can use it all the time in writing out clearly and your problem solving thinking, strategy, solutions, and it's nice you can look back and see where errors might have been made and correct them. Alright, so we put down that. Now we need to go, how many moles of oxygen for that? So we need to relate the potassium chloride with oxygen. We do that by molar ratio. There's 2 moles of this reactant to 3 moles of this product. And so this is a chemical reaction, of course, because we're starting with something and we're arriving with something new materials. That mass is conserved. That's the law of conservation of mass. And you might be thinking, what kind of reaction is this? We talked about 5 different chemical reactions. You should recognize this as a decomposition reaction, right? Decomposition reactions, decomposing to 2 other products. Okay, so we're going to put that molar ratio in here to solve the problem. We want to cancel out this and we want to get to oxygen. So we're going to have oxygen on the top, 3 moles of oxygen on the top, 2 moles of the potassium chloride on the bottom, and you should see how we did that. 3 moles of oxygen on the top and 2 of these on the bottom. That's just the relationship between these 2 in the chemical reaction, right? 2 moles of this go to 3 moles of that, and we don't have to consider the potassium chloride at this point because we weren't asked about that. It's not involved in the calculation. Now we cancel out and we have the moles of oxygen. That's what the question was about. Solve it correctly and come up with 2.48 moles. Again, we're 3 significant figures, so we round this to 3 significant figures. Okay, so now number 5. Asks us how many moles of that potassium chloride are needed to make 3.50 moles of potassium chloride. So from the equation, we're relating this reactant to this product. So don't think about that too much. We'll come to it when we're ready for that. So we first put what we have, the number that we have, on our dimensional analysis bridge. Now we want to get to how many moles of potassium chloride. So we need a ratio between potassium chloride and the potassium chloride. Right? They sound similar, but they're very different type of substances. Okay, so we look at the periodic. We look not the periodic table, at the equation here, relating the potassium chloride to the potassium chloride, and they are 2 to 2. The ratio is 2 to 2. That's what we're going to put on this line. It really is not going to make a difference. They're going to cancel out, right? But we do want to show the work. And now we cancel out the moles, and now we're left with what we want. We're asked about the number of moles of potassium chloride. And solve that, it comes out to 3.5 moles of potassium chloride. And we are very happy with that. We do a little dab there, and we win that competition. We got that page right. Hopefully you'll look at these. If you're not clear, just slow them down, think about it, see what we're doing here. It's very logical. It's a great problem-solving technique, dimensional analysis. Okay, we have one more page here. How many moles of, that's the rust thing, that's the ferric oxide, are produced when 2.75 moles of iron is reacted? Okay, that probably should be are reacted. Okay, and here's the balanced equation. We absolutely need that. But we put this on the dimensional analysis bridge first. Now we need to see the mole relationship between the ferric oxide, the rust, and the amount of iron. We go here. It's going to be a 4 to 2 ratio. And those are on the mole ratio. And then we got to decide which way we're putting that. The iron on top and the ferric oxide on the bottom, or the other way around. Well, we want the answer in ferric oxide. We want to cancel out the iron, so we need the iron on the bottom. So we put it like that, and now the mole is going to cancel out. It's part of doing the problem, canceling out. And now we're left with what we want, the answer in moles of ferric oxide, and solve the problem. Three significant figures. Don't put a whole line of numbers. That's not right. Just 3, because there's 3 there. Okay. How many moles of the ferric oxide are produced when 31.0 moles of oxygen is reacted? Right. So we put the oxygen there first. Now we look at the equation. We want the relationship between the ferric oxide and the oxygen. That's what we're going to put here. We need it in a way that the oxygens are going to cancel out. That is, one on the bottom, one on the top. So that's the oxygen you're going to put down here. It's 3 moles of oxygen and then 2 moles of the ferric oxide. Right? So that's the way we're going to put that there. The oxygens are going to cancel out. And now we do the math. 31.0 times 2 divided by 3. 20.7 moles of ferric oxide. Okay, finally, how many moles of oxygen are produced when 8.9 moles of iron is reacted? Okay, so that's the number we have. We're going to start with that. Now we need a relationship between the oxygen and the iron. We go back to the equation. There's the oxygen, there's the iron. It's a 4 to 3 ratio. It's a matter of placing them correctly on the bridge here. We want the iron on the bottom so that we cancel out to get to moles of oxygen. That's what the question is. And we come out with 6.7 moles of oxygen. And we are totally happy with that. Hopefully this was a good run through, me talking through these, and you stopping, slowing it down, thinking about it. It's really an important part of chemistry, this stoichiometry, looking at chemical reactions and knowing how to analyze them on a quantitative basis, in addition to the interesting aspects of the qualitative of seeing a chemical reaction happen. So in today's exit ticket, I asked you to use dimensional analysis to solve a problem you choose from common things around the home. It doesn't have to be chemistry. It could be just some other problem you could solve on a quantitative look, and setting it up with dimensional analysis. That is, using equivalents or ratios that you can get to a kind of a better answer, an answer that might help you solve something or give you some insight into something. And I want you to use 2 conversion factors. If you like to use more, that's fine, but then 2 conversion factors on your dimensional analysis line to get to an answer. So this is a practice in showing how you use the bridge, cancel units, and record that in your notebook page, and you'll have a Google form to fill out to tell me about it. I'm interested in seeing your thinking. And what problem did you solve using dimensional analysis? Was it that drippy faucet that you could calculate how much water goes down the drain in a year? I did that recently, and it convinced me I should fix that faucet. No sense losing all that water. Sometimes you have to make an assumption, a quantitative assumption, like we did with the counting. We said that, okay, when we're counting, we're going to call that 1 second. With the water, I know a drop of water is about 0.2 milliliters of water. And then, so I use that as one of the ratios, one of the conversion factors, that 1 drop is 0.2 mils of water. Then I put a time frame around, a time that drip to watch how many drips per minute, use that, and then got to an answer, a surprising answer. So I want to see what your dimensional analysis is. Make it interesting, make it something we can all look at and find very interesting. Okay, that's it for now.